Okay, welcome to our fourth lesson on trigonometry. This is actually, I changed the order a little bit. This is actually listed as 5.6, learning target 6, but I decided to do this before the sine and cosine law to get it do it, because it kind of goes with the other stuff. So if you try the following, what you're just doing here is putting 10 into each of these. So sine 10 divided by cos 10, sine 70 divided by cos 70. And as you go about this, you actually start to notice something, the pattern. You're getting the exact same values for each. This actually shows some of it. It doesn't prove it, but it shows that this might be true. Tan theta equals sine theta over cos theta. I say that it doesn't prove it because we're not actually putting all angles in. Where we might be very satisfied that this is true by putting a lot of angles in, until we put all angles in, we actually haven't proven it. So this is kind of an interesting concept. It goes towards a new branch of mathematics, that we haven't seen a lot of, and that's proof. It's one of the more fulfilling, challenging, but definitely rewarding branches of mathematics. This tan theta equals sine theta over cos theta is called an identity. The difference between an identity and an equation is an equation is only true for certain values. It could be a bunch, but it's only true for certain values. Identity is true for all possible values. That's really why we have to prove it, because we're saying it's true for everything. We can't just test a few to make sure. An equation would be like 2x plus 3 equals 5. An equation could also be like we've seen cos theta equals 0.2345. So there's a couple angles there between 0 and 360 that's true for, and as we get angles bigger, that'll be true as well. But not all angles equal 0.2345. On the other side, like x plus x equals 2x, all values for x will hold true for this. Tan theta equals sine theta over cos theta. This is true for every value of x. Two fundamental identities that we're going to prove is the quotient identity and the Pythagorean identity. We're going to use what we know about sine, cos, and tan, the definition of those. And so the first one we're going to start off is proving that tan theta equals sine over cos. So what we do is we start with one side, sine over cos, and we use the definitions we know, but putting it in a little bit nicer form, we write sine theta divided by cos theta. Basically what we're doing is simplifying what we have. We know sine theta is y over r and cos theta is x over r. We know how to divide fractions. We can flip and multiply. And what happens is the r's cancel out. If the r's cancel out, we're left with y over x, and that indeed is tan theta. So what we've done is just proven that. We weren't surprised to get y over x, although we were very happy to get it, because we know that we've done it right. The Pythagorean identity actually starts with something like this: sine squared plus cos squared. Although you might think that that's the reason why we call it the Pythagorean identity, and rightly that could be the reason, there's another thing that comes up in the proof that shows it as well. We've never seen this notation before with sine theta. What this really means is sine theta squared and cos theta squared, so we write it like that. We know sine is y over r and cos is x over r. We can say y squared over r squared and x squared over r squared. You can add those together because it is a common denominator. We got x squared plus y squared. And it seems that we're at an impasse. It seems like we don't really know what to do at that point. But since we're using x, y, and r, there's something true about x, y, and r. X squared plus y squared equals r squared. That's Pythagorean theorem. That comes from the circle, the exact same place that these three things come from. And if that's true, then we've actually got r squared over r squared, and the answer to that is 1. And so our second fundamental trig identity is actually the Pythagorean identity, which is sine squared plus cos squared equals 1. Now this method can be used to prove a lot of trig identities, but these two are going to go into our minds as known and proven, and we'll actually use those to prove other things. And that's what we do with proof. We actually use things that we've proven to prove other things. So what are we going to prove? We're going to look at a couple examples. Eventually you're going to use trig identities to simplify complex trig equations, but for now we're really just going to look at simple ones. Really just practicing the skill of recognizing equivalent expressions. Remember that we need equivalence, so whatever we do has to maintain equivalence. Sorry about that, another interruption. So recall the big idea of equivalence. We want to make sure that everything is equivalent. So what we're going to do is prove tan theta times cos theta equals sine theta. And I just put this little joke like tan times cos is the same as sine. If we multiply tan times cos, multiply those functions together, we actually get the sine function. And so what we're going to do to prove that is we just plug in sine over cos for tan. We cross out the coses, they cancel out, and we get sine theta. And if you notice that actually just is like you might just say, well, I'm just going to prove it like this by saying tan theta equals sine theta over cos theta, so therefore tan theta times cos theta equals sine theta. It's just a more official way to do it. This is LS means left side, and then RS is the right side. So we're just proving that it equals the right side. On the other side, we got tan squared plus 1 equals secant squared. And if we took this tan squared graph and shifted it up 1, that does mean that we get secant squared. It's the same graph. So we take tan by writing it as tan theta squared, just to make it a little bit more familiar. We know tan is sine over cos. We can say that's sine squared over cos squared plus 1. We're going to use a common denominator. We're going to add the tops together. We get sine squared plus cos squared. And we know that that's equal to 1 on top. So we can say 1 over cos squared theta. And if you'd like, you can actually write this as 1 over cos and then bracket squared and then change 1 over cos to secant. But it's okay just to say that that's equal to secant squared. And that's the right side. Just one more. But look at this one. I always love these ones with fractions because they seem to be challenging, but if you know how to deal with them, they're not so bad. And it really just how we deal with fractions in general. We're going to make a common denominator. And we see the common denominator is very close. 1 minus sine, this is 2 1 minus sines, this is only 1. So we really notice that first. So we're going to just create the common denominator by multiplying top and bottom of the left side. So we're going to take the left side and multiply top and bottom by 1 minus sine. That way the bottom has a 1 minus sine theta as a common denominator. Now we're really just trying to make sure that if we do some quadratic manipulation, that we're getting the same thing on top here. If we expand this out, we get 1 minus sine squared. It's not trivial to say this, but if you haven't done it before, but after a while, you can say this right away. If you know sine squared plus cos squared equals 1, this maybe has something to do with that. You can actually put the sine squared on the other side. You get 1 minus sine squared, and we can put the cos squared on the top, and then it's proven it equals the right side. So some practice questions, 1 to 3 in the Nelson book, they're really good warm up questions to just see what expressions are equivalent. 5 to 8 is really your practice with proving. Now you can look at the assignment here. This will be handed in on test day. I'm requiring you to actually make your own trig identity, and the best strategy to do that is to start with a top and do a whole bunch of things to it, and the other side will be your other side, or the bottom will be your other side, and the work you did will be your proof. We just have to make sure that you understand the equivalence to be able to hit all of these criteria.